Broadcasting from the commodity capital of the world, Zurich, Switzerland, this is Insider's Guide to Energy.
This edition to Insider's Guide to Energy is brought to you by Fidectis. Go to www.fidectis.com for more information.
Welcome to Insider's Guide to Energy, and today brought to you by a new constellation of co-hosts. With me today is Jeff Mccaulay. Welcome, and it's going to be great to co-host with you. Welcome to the show.
Yeah, Johan, I'm super excited after listening for many months to get to work with you directly while Chris is out. So yeah, very excited for the topic today as well.
Maybe we should just clarify as well. Both of us are not new to the show. We're still part of the Insider's Guide to Energy team, and it's going to be really, really interesting to this one. So how you been this week?
Great. And I will say that the topic for today being interconnection, this seems to come up in every other conversation, at every conference, at every speaking occasion. Reliably, at some point, a speaker will stand up and say and complain about interconnection queues. So being an insider's guide, it feels like about time that we get into this. And I can't imagine a better guest to guide us through this on the distribution system than Astrid Atkinson. So really excited today.
I think you're totally right. And I look forward to this show as well. And I think not only from the actual interconnection part that we're talking about and that we will kind of dig into a little bit, but also the journey of this. You know, we talked about the Insider's Guide of Energy, of being the sustainable and the energy transition, but how digital also play a role in this one. And with the background from the tech industry into the energy industry is also something I want to dig into a little bit and have a few questions. But I think there's so much to talk about, so I think we jump straight in. So Jeff, why don't you just give an introduction to our guest and also a little bit around what we're going to tackle today. You mentioned interconnectivity, but please.
We are joined today by Astrid Atkinson, the CEO and co-founder of Camus Energy, a provider of grid-aware DER orchestration. She has a deep technical background in large-scale distributed systems architecture, including helping launch Google's cloud. So really thrilled to have Astrid with us today. And the topic that we want to dive into is really around interconnection, because in the US, in order to reach targets for 2030 of 80% renewable energy, we're looking at terawatt scale DER deployment. And that just can't happen if we've got 12 to 18 month interconnection queues. And so first thing I want to separate out, a lot of that is based on the utility scale bulk power system interconnection. We're going to talk about the distributed side of things. And Astrid, welcome to the show. Thanks for joining us. Looking forward to talking to you more.
Yeah, Johan and Jeff, it's a pleasure to be here. Really nice to meet you both.
So help us understand, I guess, how do you frame the problem of interconnection on the distribution grid?
Yeah, I mean, I think firstly, the delineation that you just drew between the portions of the interconnection challenge that are really about connecting new sources of generation to the bulk grid is a lot of what people think about when they think about interconnection. And that's really driven by a need to rapidly turn over our generation fleet from fossil to renewable, get a lot more large-scale renewable generation and storage projects onto the grid, and deal with the very long queue of projects that are in the backlog. So this is a really large challenge and tends to affect a lot of folks that are working in the broader energy transition space because they're doing development of solar and storage or wind projects or geothermal or new tech projects. And this is a very significant issue around generation fleet turnover and meeting increased demand. But it's only about half of the challenge. And as we know, on the transmission side, a lot of a lot of the delays and challenges are really kind of focused around large scale transmission build out and enhancements to the to the bulk grid and the physical infrastructure of the transmission system. The other half of the problem is on the distribution side, and that's primarily where I work. Um, on the distribution side, we've got really a couple things going on. Firstly, when you can't get capacity from bulk resources because of transmission challenges, one of the things that you can do is look to develop energy projects locally and connect them to the distribution system. This is something that's happening for a number of reasons, everything from individuals, communities, commercial and industrial customers, and utilities looking to do local generation development. And then the other side of the challenge that I think is really underappreciated is load. Load also goes through an interconnection process for larger loads. And when we look at the challenges associated with electrification, that's all loads. They've got to get served somehow. So they have to get connected to the distribution grid. And the distribution grid needs to be able to actually support like all of this load growth that's coming online. And that's something that we're just in the early days of, and it is a growing problem, and it's going to be a pretty large one. So that's kind of where I wanted to focus for our conversation today.
Yeah, it's a great point. And we heard this come up as well in a previous conversation with microgrid developers that absent any distributed energy, just upgrading the electrical service to a warehouse, maybe including electric forklifts or maybe electrifying heating and cooling, these are challenges separate from distributed generation. But we also heard it for EV chargers, which is also load, but we think about it as controllable load. So this is really important. And, we all engage on from time to time with utility bashing, but I think with a sympathetic framing here, the utilities are trying their best. They want to serve load, they want to do so responsibly. So it's all about how can we collaborate? Are there tools available to utilities to help them through this analysis?
Yeah, I think it's really important, firstly, to frame, what does it look like when we see challenges associated with connecting loads? Now, firstly, like that does go through an interconnection queue for a distribution utility. It's similar to or typically a part of the process that utilities use to connect distribution connected generation as well. But the stuff that goes through that queue is usually really big loads. So that'll be things like data center loads, warehouses, factories, these kinds of things. I think it's probably useful just to like kind of share a couple of perhaps anecdotal, but maybe useful kind of stories about what this looks like. So I think most of us have probably gone through the experience of needing to add something in our own homes, maybe like an induction cooker or an air conditioning unit or EV charging or something like that, and kind of running into the problem that like the panel is full. Like I need another 50 amp breaker, another 20 amp breaker or whatever for this load. And it's, maybe we don't have that capacity available in the power drop that's already coming into the house. And then, you're ending up working with an electrician, potentially with the utility to get increased capacity coming in. That's something that's moderately familiar to lots of people. And when we look at challenges associated with load growth beyond just residential, like that's what it looks like, but at much larger scale. So one thing that was really striking to me was a month or so ago, I was chatting with a bunch of other startup founders, many in the kind of physical infrastructure and manufacturing space. And the main topic of conversation amongst them was challenges associated with building new manufacturing facilities, even for testing. And it wasn't anything to do with supply chain or workforce availability or funding or anything. They were like, man, I really need to find a place where I can get enough power to build a factory. And they're comparing notes. They're like, oh, I think there's some extra power available, like over in some facilities in Fremont. You should check it out. We're opening an office in Ohio. Oh, do you have people there? No, we could get power. And that was really striking to me, because for that to be the thing that is on the top of the mind for a bunch of entrepreneurs, it's like a pretty big deal, right? Like those are big decisions, setting up new offices, setting up new facilities, new areas, all of these things. It's increasingly driven by a difficulty of just getting power. That's also really, really true in the data center space. Just for comparison points, right? When I was at Google for about 15 years prior to co-founding this company. Um, the typical data center footprint size for a new facility was in the kind of 50 megawatt range, which is a lot. It's pretty big. By the time I left, it was in the probably 1 to 200 megawatt range. Um, Kind of checking in on folks in the data center space now. It's really typical for a new data center footprint to be looking for a gigawatt. That is a hell of a lot of power. And every place those facilities go in, like in and of itself, that's also driving really significant system challenges.
So, being European and maybe not an expert on the US markets around this, help me to understand how is this then addressed, and who would actually, I wouldn't say own this, but lead this. So you're saying that we want to build something in Texas or in somewhere else in terms of a not only a new battery factory, it could be anything of a construction that is energy heavy, data centers being one of them. But who actually owns this then? Who can provide this, even though it's a big task or big ask? But because sometimes I think that the responsibilities around the energy ecosystem falls between chairs and everyone kind of points at one or the other. But where do you see this? Where does the big challenge lie?
Well, the space that I'm most familiar with on the load side is the data center space because it was my life for quite some time. And so, firstly, a lot of this happens on the consumer side. So, for things like data centers, power availability is actually probably the largest factor in choosing where to site a project. Network connectivity is probably the second largest, but increasingly, folks like Google or Meta or people who put in big data centers will do that in places where there's no network connectivity, and they'll solve the network problem because it's a power that's hard to get. So they'll typically have, kind of a range of options for where they might look at siting projects. Back in my day, they were small enough that they would do things like look for places where aluminum plants had been turned down, knowing that there was already large scale power connectivity available to the site. The industry has scaled beyond that point, but that was actually a really common thing for Google, kind of back in like 2004, 2005 when I started working there. And that's a big part of why they chose like their Dalles facility in Oregon, for example. So they'll typically have a sense of, a range of places where they can put facilities. They will try to get very large power allocations so that they can build out more capacity later. They'll often only build to a fraction, maybe a couple hundred megawatts of that gigawatt allocation now, but reserve the rest for later. So it's not uncommon to have a big data center facility in the middle of nowhere next to some cornfields that will eventually be more data center facilities. That's in Iowa, that's kind of what they look like. Um, but the consumer will have a sense of where they want to place the asset. They will then typically need to work with the utilities that serve those areas to try to understand optimal placement. This is the first place where you run into trouble because most utilities don't have the tools to actually really tell them what optimal placement would look like. So, like anybody coming into the interconnection queue, they're often left. They might have a verbal conversation with the utility about where's a good spot, but then they'll like scope out their project. They'll be like, okay, what about this area, this plot of land? I'll put in the queue request to the utility. The utility will take 12 to 18 months to consider it, and they'll do those in a few different places and see which ones are successful. And you can kind of see, like, really early on, the same inefficiencies that we see in any other part of the interconnection process right there. Like, it'd be pretty nice, actually, if especially a larger utility could be like, anywhere in my 8-state footprint, these are the like 14 locations that could serve your needs. And that's kind of not how that works. And you'd kind of expect that it would be. So that's kind of like step number one. As to who owns, once the off taker or the consumer has really started to think about their placement, um, it is typically a process of coordination with the distribution utility, firstly, to get connectivity. Sometimes it'll hook into the transmission side. Next, they need to think about capacity. A lot of these data center facilities will go with clean energy requirements. So they'll also be thinking about their ability to either procure sufficient clean energy resources through PPAs or RECs, or for those who are thinking about 24/7 clean power, then they need to think about like locational availability of green energy. And that adds an additional layer of complexity as well. And so, to your point, there are multiple constituents in this, whether that's distribution utility, regional transmission authority, ISO, et cetera. And that is part of the reason it takes a long time.
Then why is it so hard for the distribution utility? And what tools are available to start to help these distribution utilities work faster through these challenges?
I think it's a really good question to ask, and there's a couple of answers to it. And firstly, this is a problem that has been growing for a while, but it's growing exponentially, which means that last year it wasn't such a big deal, and the year before it wasn't, it was even less of a big deal. So when an exponential problem shows up on your doorstep, it feels like it just suddenly appeared. And I think to some degree that's what's happening here. Most utilities don't really have very great integrated planning and kind of data management tools that would let them um, really deeply understand in a forward-looking way, where my capacity availability is, be able to publish and share that with multiple constituents. Sometimes that's kind of a data availability and kind of data capability issue on the utility side. It's also kind of a tool chain issue. The existing tools were meant to support, firstly, smaller interconnection requests and less of them. Usually it's a human workflow rather than an automated one. So, they'll have a planning team that fields these requests. And last year they might have fielded 5 a month, and now they're seeing 50 or 500 a month. And so those human workflows are not keeping up. Those are great opportunities for automation and for software-based solutions. But the utility space doesn't necessarily have as much muscle on software innovation and kind of rapid software adoption as many other industries do, for any number of reasons, which I'm happy to have a longer conversation about if you want. And that really is a challenge when you have new problems that are really data and computation problems, and you don't really have the foundations and kind of organizational experience to do that well, quickly, at scale, and differently. That can be a little bit more challenging.
Hmm. And we've heard that there can be some finger pointing between the distribution utility and RTO. And, are there a set of rules here that are constraining that decision making envelope? And is there a way in which, in a world of flexible load, in a world of distributed generation or energy storage, that we can have a more dynamic way of dealing with these hard constraints on the distribution system?
Yeah, there are a lot of constraints and kind of uh, regulatory constructs and rules and so forth that absolutely impact these conversations. And that's the part that I'm not going to get into, and you should get a different guest for that. But in terms of, what are your axes of flexibility on the demand side or on the distribution side? Um, I think firstly, it's kind of interesting to observe that the way that we have typically tackled interconnection issues in the US, both from a generation and a demand standpoint, is from the perspective that the generation or the demand request is inflexible. So it's basically like it is this big. It is, 10 or 15 or, whatever unit you want to kind of measure in. Um, and you're effectively asking the utility or the RTO a yes or no question. Can you support, 10 megawatts, 5 megawatts, 2 megawatts, whatever? And they'll tell you yes or no. What we don't have is a really good kind of widespread and well understood capability to discuss axes of flexibility. Like, what if it was a 5 megawatt load, but most of the time it's only, 3 megawatts? We've got, maybe 2 of headroom. You might, under normal circumstances, sort of look and ask the question, well, could you build a smaller facility? And then that's another 18 months to, plan the new one. Or other countries, particularly in Europe and in Australia is the one that I'm most familiar with, have really started to look at models for basically flexible interconnection on the distribution side. So this is really kind of similar to looking at like a dynamic line rating type model on the transmission side, where you're basically saying like, okay, here's the overall capacity of my system. My system is built for n+1 or n+2 capacity at any given point. So it's the idea that like if we were to lose units of generation or transmission capability or distribution capability, that we would have enough overhead to continue to serve under normal conditions. And that's typically the way that system planning is done, and it's very inflexible. So when you're looking at connecting a load, you're not looking at connecting within the context of the normal load on that part of the distribution grid, plus the normal load for the new load being added. You're looking at the worst case scenario. What is like the 10-year peak for this area and the absolute maximum that this new thing could ever do? That when you ask the question in that way, you need to build a lot more grid to be able to say yes, or you need a much smaller facility. The model, there's a couple of models for managing this. The one that I really like is the one that's coming into wide use in Australia. So they have been working collectively across the research space, both on the academic and kind of equivalent of the DOE side, as well as within the utilities and the market operator on effectively dynamic interconnection models. And one of the constructs that they use for this is this idea that you could monitor the usage of any part of the distribution grid and then give a dynamic capacity allocation to either generation or demand participants, and use that to manage your like 10-year kind of peak scenario and make sure that all of the operators can share the available capacity amongst the resources that are getting connected. This goes under the general heading of dynamic operating envelopes. And it's well past the pilot phase in Australia. This is something that's being broadly rolled out across all of the network operators in the next 2 years.
So it's an interesting part, kind of looking at the larger scale around this, and there's a lot of things that goes in from all these different ones. And then we, as I mentioned in the beginning, we also have then the digital kind of transformation as a part of this one. I think that's also where you come in with Camus Energy as well. So maybe a little bit of a description or a kind of a where do you fit in as in this equation, and how do you provide value to solve some of these things?
Yeah, so probably helpful to give a couple words on my background. So as I mentioned, I was at Google from about 2004 onwards. And when I joined Google, that was when they were in the process of transitioning from kind of a traditional computing model where you basically kind of put work on a computer. If you want more work, get a bigger computer, to a distributed and cloud-based computing model. That was entirely new in the industry at the time. It was a new idea. It had been tried in kind of academic settings in a couple places, but Google was one of the first places that this work was really done at scale. And so when you mentioned from my background that, I helped build Google's cloud, I did work on Google's external cloud, which I think is probably about the, fourth or fifth most popular in the industry. But what I helped build for Google was the original cloud computing model, like the one that powers all of Google's internal operations, where we went from sort of putting work on one computer to spreading it across millions that were separated by unreliable networks, where the servers themselves were also completely unreliable. For scaling and cost reasons, Google was buying very unreliable hardware at the time. They were getting the cheapest they could, had known manufacturing flaws. They would, buy stuff that was returned. They would buy off the back of trucks. The network wasn't reliable either. They jammed it into data centers that didn't have space at the limit of power availability. And so, they would, back in the day, have racks that caught on fire. It was pretty normal that, they would have these like super stuffed serving racks that were burning hot, running fans to push all the heat into the other side of the colo facilities that they were in. And what that produced was a computing environment where they were trying to do two simultaneously impossible things. One was spread work across many thousands of computers and still be able to get your, web search answer back in under a second. The other was to build a system that was more reliable than the consolidated serving ecosystem that had preceded it. So they were still aiming for 5 nines of reliability, like 99.995% or better, which is about 3 minutes of outage per year, which is utility grade reliability. And that was very unusual in the tech industry. And their strategy for this was basically, we'll fix it in software. The cloud was invented to support that model. And it wasn't for its own sake. It was because they were trying to incorporate unthinkable, unheard of amounts of data and be able to do very complex calculations in real time and provide a kind of value and a kind of experience to users that nobody had ever done before. And when we think about the role of digitization in the grid space, that's also the real value that I see in bringing that transition to the grid. Because when we look at the challenges of, how are we going to manage the distribution grid when it's got like millions of active participants or billions of active participants even, how are we going to manage it when it's, full of two-way flows, complex switching states, complex distribution automation, too big to run the physics models, in minutes or seconds, too complex to manage in the ways that we manage the very dynamic transmission grids of today. We're going to need more computers. There's a lot of data to bring in. The grid data that's out there is by utility standards a lot. If you look at like 15-minute data points from meters, for example, existing utility technology really struggles to incorporate that. But the big tech systems, the cloud systems that we built to support, those, kind of billion participant systems will typically handle trillions of data points a day, not the sort of, millions that you look at when you look at meter data. We have really good technology for managing very large data landscapes like this. Being able to put those to work to support these grid transition challenges will change what's possible. And so, what do we do? And the reason that I got interested in this space in the first place is partly because, my background in large systems infrastructure, and also I did a lot of work in operations models at Google and helped lead up a lot of the early work on basically how do you get 5 nines of reliability out of a bunch of junk parts, is kind of uniquely useful in contexts where you need utility grade reliability. What needs utility grade reliability? The grid. That was why I got interested in it in the first place. The more I dug into it, the more I saw opportunities for bringing that kind of cloud scale computing capability to solving some of these really, really complex system management problems. They're not the same problems, but those tools are really going to help us out because we need to be able to do things like calculate a dynamic capacity envelope for basically every EV, or at least every EV charging facility, in an environment where need to do that is accelerating exponentially. So kind of a long answer, but that's the background. In terms of what my company does, I mentioned we do highly grid aware orchestration. We basically do full scale data integration for every point on the distribution grid, both the utility data sources and third party. And we use that to understand, firstly, what are the goals associated with managing resources that are out there. These are typically DERs because those are the things that you control at scale. And then translate that into orchestrative control, which what I mean by that is it's not just looking at controlling a single asset, but looking at controlling fleets of assets within any particular locational context on the grid to accomplish goals. So not overloading a feeder, not overloading a transformer, managing conductor capacity in an automated way, while also being able to dispatch those assets for market participation or peak shaving or carbon reduction or whatever else you want them to do.
And what do you call that? Is that DERMS, ADMS, DSO? There's a alphabet soup here, and maybe you can help us decode the different terms.
So we broadly describe it as it's kind of DERMS plus plus, so distributed energy resource management system. But we do a lot more grid awareness to inform that management than would ordinarily be the case. We also focus upstream of where the majority of DERMS offerings in the field focus today, which is typically on, like I said, it's kind of managing the assets. to really focus on that kind of multi-asset, multi-entity orchestrative control. So it'll include usually things that are under direct control by the utility, but also fleets of customer assets, VPPs, et cetera. I actually prefer to think of it, and we'll describe it to folks in the utility space, as a platform to enable a distribution system operator model or a DSO model. And that's really kind of taking this idea of managing the distribution system as a real-time orchestrative dynamic platform for many assets to conduct business on, similar to the way that an ISO manages the transmission system of today. So for utilities, I describe it as a DSO platform. For folks who are not as fond of alphabet soup, we'll go with the acronyms they're more familiar with.
So looking at that, one thing that I've always looked upon when you start looking at data management, so be that in one industry or the other, is, and especially here when you have something kind of a cross-sector interconnection as well. The utilities is one thing, but now you're starting to get the automotive industry, you're starting to get other industries into this as well. How do you manage this in terms of standards, interoperability? For me, it looks like a spider web of just definitely not connected or interconnected.
Yeah, I mean, I think it's really helpful to look at models that have worked well in other industries. And I think telecom is a really good example of how this type of infrastructure challenge can evolve. Um, you know, at, Today we have a high capacity, low cost, nearly universally available telecommunications system that is, cheap enough for most folks to have a, $20 a month unlimited capacity plan, and all the cat videos are, you know, you know, uh, learn from home university courses, or whatever it is that they're looking for. That didn't happen overnight, and it didn't start with developing standards for building that system. It started by kind of laddering up from the capabilities, firstly, of the wired operators and then the wireless operators, kind of multiple generations of attempts at standards and coordination amongst providers. Couple of, kind of breaking changes from a technology perspective. But ultimately, when we look at things like developing the 5G standards, we came to a place where many vendors worked together to start looking at ways to build standards and standard reference implementations and so forth that could serve the whole industry. Automotive has kind of gone the same way. Building computing technology for cars was something that individual manufacturers did, often honestly, struggling because I think it can be really difficult to get great software in industries that are primarily focused on other things. Um, but the automotive industry's gone through a lot of this, built a multi-vendor consortium, started to look at joint standards, started to look at like joint open source and platform implementations. And that's helped to accelerate everybody. So we'll go through that process with the grid as well. But I think that it's really difficult to start by just developing like the universal set of standards that are going to fix everything, because that's in and of itself a 10-year process. Um, I do think that there's a ton of value in having standards, and we have a lot that are out there already. Thinking about how to put those to work, for example, like 2030.5 for universal inverter control is going to make it a lot easier to reach out and talk to inverters from a lot of different manufacturers. That's really helpful. It still doesn't really solve the problem of like, how do you go from having a decent but not perfect understanding of the grid to telling all those inverters what to do. But that's where I think like the role of cloud-based big data technologies is really helpful. Because if you could at least start by integrating the data from all those inverters in like a sensible real-time way, putting it together with the data that we can also integrate from all the meters, all the SCADA points, et cetera, and then beginning to make decisions about it. Starting with some visibility is a really good place to begin. And this is something that I think we've seen also be replicated in other folks that are bringing software approaches and sort of software-based systems approaches into places like GovTech, MedTech, et cetera, kind of out of the big tech space.
Astrid, help us think about the future here as we're thinking about these other markets that have gone through a similar evolution. Maybe the first phase is monitoring and visibility, And the second phase is your DERMS++, where you can start to control maybe for extreme events or demand response. What does it take to get from there to this dynamic operating envelope where utilities can trust the control enough that they let new assets on the grid and have a more flexible operating regime?
Yeah, I think that trust point is really the key part of that. Part of this is a technology problem, but more of it is an organizational process, capability, and trust issue. Um, a lot of what I did in my early work at Google was really thinking about how to build systems that support a transition to very large scale distributed computing infrastructures. Only about half of those are software systems, the other half are human systems. How do you build operations capabilities and kind of systems engineering and infrastructure capabilities that can provide reliable service on top of a bunch of junk parts? Um, and part of that is building the dynamic management and monitoring capabilities that let you see and then manage what's happening on the system. And part of that is also building an operations capability that can reason about and also honestly help to design those systems in a forward-looking way. So there are probably really two things that were key to how we approached that when we were kind of inventing distributed systems operations at Google. Um, Firstly, having the folks responsible for operations also be the ones responsible for systems infrastructure and systems design was the absolutely core part of Google's approach that differentiated them from everybody else in the industry. And that was the team that I was part of and helped to lead up. That was their systems reliability, or sorry, site reliability engineering group. And it was a hybrid operations and engineering team that was like literally responsible both for keeping the site running. Held a pager, I carried a pager myself for 5 years, and was the first line and the last line of escalation for site issues, and simultaneously responsible for systems architecture and working with the many, many, many engineering system or software engineering systems or teams that were building infrastructure to help us grow. So that tight feedback loop between operations and new technology deployment is really important in any space that is changing rapidly because it is very, very hard to come in with a more traditional kind of you know, uh, physical infrastructure, like systems engineering approach and say like, okay, we've spent 5 years scoping out the system. We're going to spend 5 years building it, 2 years deploying it, 2 years testing it, and then we will have solved this problem for the next 50 years. That's not really how software systems work or kind of big data or distributed systems work, because the problem space is changing really rapidly. So you need that tight feedback loop to make sure that you're iteratively delivering systems that work well and that that is being very rapidly informed by the people who are responsible for keeping them working. So that human system is a really big part of that. The other thing from a technology perspective that's critical is to do that, you have to be able to see it. Um, when I started working or looking at transitioning into the grid space, which is 5, 6, 7 years before I left Google, I thought initially that it might be helpful to bring in some of those like very large scale real time load balancing technology capabilities. When I started talking to people at utilities, they were like, "That sounds great. We don't have that many resources today. Also, like manage it. Like we can't even see it." Um, and so that for me was like a really big reset. It's like the core of building operations team capabilities in my previous life was being able to have a decent real time view of the whole system. And whenever we take that type of discipline into other fields, like health or government or whatever, that is always the place where like folks with my background would start. It's like, do you have monitoring? Can you see what's happening? Do you have like handle on whether things are working or not working in the field? So that capability, I think, is really the most foundational piece for all the rest of this.
So, how do we get to a point? Is there a way to get to a point of optimism? Because if I'm putting my utility hat on, I'm sitting here listening and saying, okay, so I have constrained budget. I can't afford the former Google network optimization team. I can't hire people. I'm constrained by the PUC in terms of what I can do in terms of rates. And I can't even see, let alone control, let alone change my operating window to be dynamic. Is there a catalyst that can help this transformation? And I know that some of this is on the regulatory side, but are there things that give you hope in conversations with utilities that this is achievable with all of the constraints of the utilities that maybe didn't exist in Google?
Yeah. So I think, like, honestly, there's a really good foundation already in place within the utility industry for doing a lot of this work, right? Now, firstly, folks who work at utilities are really smart. They're super good at what they do, which is keeping the lights on. And when they have challenges that are confronting them that actually affect keeping the lights on, they are very, very, very good at figuring out how to solve those challenges. So many folks at utilities have seen this coming for a long time. They've been thinking about the capabilities they're going to need. And investment in this space has been happening for at least the last 10 or 15 years, right? Like, we are pretty far down the road of making sure that we do have the instrumentation out there that could be the foundation for that visibility. Most utilities have done smart meter deployments. Most utilities have made investments in upgrading SCADA systems and getting the system instrumentation online that can help them do smart management. Lots of them have put smart grid initiatives in place that increase their visibility. Um, Most don't yet have really comprehensive ways to put that data to work. That is a technology problem, but not an insurmountable one. That's where I think looking at like places like the telecom industry and the computing industry can be really helpful, because like we honestly have great data platforms out there and great approaches out there for bringing lots of data together and making it actionable. That is not new technology. It's not novel and it's not risky either. It's honestly really boring technology. If you want to do something big, assembling the parts of the solution from boring technology, it's really the way to do that. One of my advisors, in a different context, used to say that no grant application could have more than one or two pieces of magic. I think no very large scale systems transformation project can have more than one or two pieces of magic, but we don't need magic. We just need to put what we know to work. So, taking advantage of those data sources that are out there, those investments that have already been made, is a really big part of this. The second piece is that when we think about like how do we rapidly adopt these technologies and how do we pay for them, it's most helpful to me to do that in the context of looking at the costs associated with solving the broader electrification and grid expansion challenge. It's going to be really expensive if we have to build new grid infrastructure to interconnect every data center or every fleet charging location or every neighborhood. But if we look at the costs of smarter systems management alongside the costs of building physical infrastructure, there's a lot of room for optimizing and being really smart and efficient about how we spend that capital. And so I think like the shift that really needs to happen is just making a little space for the folks at the utility to start to think about that broader set of investments in the context of both distribution expansion and smart grid capabilities, out of the same kind of common budget and out of the same kind of common goals. Once we connect those software capabilities to core business needs, things can change really quickly.
Do you want to wager a date at which we can get an 18-month interconnection queue down to 18 days? I mean, I'm not talking about your gigawatt data center. Obviously, that's going to take a longer time, but we are hearing complaints even for a 20 kW EV charger is double-digit months. Do you have a vision where that can get down to less than a month? And when would you wager that might be possible?
I mean, I think this is where the Australian model is really interesting. I wish I had off the top of my head stats for size of interconnection queue there, but a lot of the work that they have done on looking at cooperative planning and dynamic capacity management has been focused around this challenge. Um, Queues there are on the order of months, not years. And that technology rollout, having been piloted successfully, is slated to complete over the next 2 years for every network operator in Australia. Um, no, that's a little bit of a different environment where it was, a little bit easier to be like, hey, everybody go ahead and do this. But at the point where there are technology solutions that have been used by one or two utilities successfully, that's actually a place where regulatory action can really help, because then the regulators can just say, look, there are some successful proven solutions in this space that can really help. We know what that looks like. Now everybody please go adopt that. And so I think we'll see that start to happen really rapidly once we've got some good proof points in the US with the large utilities where this is a really big challenge, because that's what everybody's looking to for examples.
I thought that was a fantastic end of the show. We're coming up to time, so I would like to thank you, Astrid, for coming on. I thought this whole intersection between bringing the technology and knowledge and lessons learned into the utility industry is fascinating, and I think it's kind of a theme through the Insider's Guide to Energy podcast as well. So I thought it was really, really interesting. Certain parts, obviously, for me, as not deep into the energy, I was still struggling to understand, but you explained it very well. So I take that with me coming out of this meeting. So once again, Astrid, thanks a lot for joining. Jeff, pleasure to be co-hosting this episode with you. For our guests, you have listened to another episode of Insider's Guide to Energy. If you don't follow us on social media, please do so. Engage, share, and we'll speak to you next week. Bye-bye.